radiological characterization is of paramount importance for nuclear safeguards. Unfortunately, some radionuclides cannot be easily detected and measured. Do you know why these radionuclides are hard to measure? How should we deal with them? This is what we are going to learn in this lecture. Concerning their measurement, radionuclides can be split into two main categories: easy to measure and hard to measure. Those belonging to the first family have at least one characteristic gamma line that allows the easy measure by gamma ray spectrometry. This is a non-destructive measurement if it is directly performed in situ without collecting any sample. Examples of radionuclides belonging to this class are cobalt-60 and cesium-137. Easy to measure radionuclides are also called key radionuclides. In fact, they can be easily measured in a large number of samples and used to estimate some hard-to-measure radionuclides, thanks to spatial correlation factors, the scaling factors. On the other hand, the radionuclides belonging to the hard-to-measure family do not own easily measurable photons, as their energy or branching ratio may be too low. Examples of radionuclides belonging to this class are pure beta and alpha-emitting radionuclides, like plutonium-241 for betas and plutonium-239 for alphas. Their accurate quantification involves a destructive measure, since it requires the collection of samples and lengthy and laborious radiochemical separation procedures. But why destructive techniques are required in this case? A first answer to this question is given by radiation-matter interaction. While gamma rays of proper energy emitted from easy-to-measure radionuclides can easily come out from the matrix to be measured, soft X-rays, alpha and beta particles don't. In fact, being them low-energy photons or charged particles, they strongly interact with matter, so that they are stopped by the matrix. This fact explains why hard-to-measure radionuclide separation from the matrix must be always performed if they have to be determined. There are several methods to separate the analyte of interest from the matrix, depending on its physicochemical characteristics. In the easiest case of liquid samples, the separation can be performed by evaporation of water or precipitation of insoluble salts. In both cases, the analyte remains in the solid residues. If the analyte of interest is volatile, like tritium, it can be removed by distillation and collected by proper trapping solutions. When a solid sample is concerned, other methods can be exploited, such as the so-called acid digestion. In this case, the matrix is dissolved by a proper mixture of acids, often with the help of a heat source like hot plates or microwave ovens. Alternatively, the sample can undergo incineration in a muffle or alkali fusion to destroy the organic matrix. In all these cases, both ashes and solid residues are then dissolved by a proper leaching solution to recover the analyte of interest into a homogeneous solution. Once the matrix has been removed and the analyte convoyed in a proper solution, a further step is required: separation from possible interfering radionuclides. This step is mandatory for beta-emitting radionuclides, as they show a continuum energy spectrum. In fact, if several beta-emitting radionuclides are present at the same time, the spectra would overlap, hampering the determination of the desired analyte. Also in the case of alpha-emitting radionuclides, this purification step is important to remove any possible spectral interferences during radiometric measurement. Beside matrix removal, the need for interfering radionuclide separation is the second answer to the former question. Why destructive techniques are required for hard-to-measure radionuclides determination? There are several methods to carry out this separation. Among the simplest ones, the selective precipitation of insoluble compounds of the element of interest can be pursued. For example, iodine and chlorine can be effectively and selectively precipitated as silver iodide and chloride. The compound precipitates once its solubility product is exceeded. Here you can see the solubility product formula, being A and M the anion and cation concentrations, X and Y their charges. In some cases, a similar approach called coprecipitation can be used. In this case, the radionuclide is precipitated by a non-isotopic compound. For example, radium-226 may be co-precipitated as isomorphically substituted mixed crystals of barium sulfate, since barium 2+ belongs to the same group of the periodic table. Another co-precipitation mechanism exploits ion exchange absorption on the charged surface of a precipitating compound. For example, iron hydroxide can co-precipitate high-valence cations, such as transition metals and actinides. To selectively separate one analyte present in the aqueous phase together with some interference, solvent extraction can also be used. This technique allows to selectively transfer the analyte into an immiscible organic phase thanks to a molecule that is called ligand. This molecule selectively chelates the analyte and forms a complex soluble in the organic phase. Another technique to purify a solution from interference is ion exchange chromatography. Thanks to the functional groups owned by anion or cation exchange resin, some anions or cations are retained on the resin by Coulombic interaction, while others are flushed away. As you can see in the formula, the selectivity of the ion exchanger towards specific analytes is given by the ratio of its concentration in the resin and in the solution. Both in the case of solvent extraction and ion exchange chromatography, the analytes are then released in an aqueous solution for further processing. Lastly, the most effective and selective extraction chromatography technique has been recently developed. It is based on the functionalization of chromatographic column with ligands that selectively form complexes with the analyte as in solvent extraction. It is particularly used for actinide separation. In this lecture, we have discovered the existence of hard-to-measure radionuclides, important for nuclear safeguards, and we have learned why their determination requires destructive analysis. Moreover, the basic principles of matrix removal and interfering radionuclide separation have been briefly summarized. The next step are source preparation and radiometric analysis.